So what we're going to do is we're going to look at how we could explain each of the following in terms of, so here we have a situation where we're asked to look at the impact stirring a solution on the rate at which a solute would dissolve. Well, the first thing we're going to do is we're always going to come back to our idea that our rate of our reaction is proportional to our total number of collisions times our fraction of effective collisions. And when we look at our scenario, we want to look at which one of these two things it will impact. And so we know that stirring of a solution will increase the motion of the particles. And so since the particles are moving more, what will happen is they'll have a greater chance of colliding. So therefore we can say this will increase the total number of collisions. So since they're colliding more, our total number of collisions has increased. As a result, the rate of the reaction will increase. We'll look at a second scenario. We're going to fry donuts at a temperature lower than advised. So again, the first thing we want to do is we always want to make sure that we state the parameters that we're going to use, right? So we know that our rate is proportional to our number of collisions times our fraction of effective collisions. Now, temperature is one of our unique properties, and that affects both our total number of collisions and our fraction of effective collisions. So therefore, we have to comment on both properties. So the first one, or the easy one to deal with, is the total number of collisions, right? So we can say temperature is a measure of their average kinetic energy. Of particles. So the lower the temperature, the less particles move. This will decrease the number of possible collisions, resulting in a low rate of reaction. Now for our second part, where we talk about our fraction of effective collisions, we want to use our Maxwell-Boltzmann distribution, right? So we have our kinetic energy, our number of particles, and we can show our two lines for our two different temperatures. We know that it follows an approximate normal distribution, and then I can add a second line to represent a different temperature. It doesn't matter which ones I put on here first. Then I can label them. So this one, the one with the peak further along with a higher average, because the peak is where the vast majority of them are, this would be my higher temperature. So this would be T2, for example. So it would be T1. Now onto this graph, we could then go and add the next important line, which would be the line that represents my threshold or activation energy, and I'll label it as well. And remember, this is the minimum energy required for a collision to be effective. I can also just highlight the two different regions. And now we can use what we see in this curve to explain what's going on. And what we can say is that at a lower temperature, we can see that there's far fewer particles, right? In the purple here, by lower temperature. With sufficient energy for an effective collision. Right? We can see with our red here, at a higher temperature, there's a greater fraction. Okay, so now if we come back to the question at point, since my lower temperature has a smaller number of particles with sufficient energy for an effective collision, I can say that this will result in a lower fraction of collisions which are effective. As a result, the rate of the reaction will decrease.